The title of our project is The Effective Mass on the Period of a Simple Pendulum. This lab, as well as all of the procedures that follow, were completed by myself, Nicole Petrasan, and Samuel Vargas. As we looked for topics to do our lab on, we all decided that the concept of a simple pendulum interested us. While we had looked at it earlier in the semester to find the acceleration of gravity, we wanted to look at a different aspect of it. This is how we decided on the topic of the effective mass on the period of a simple pendulum. The objective of our project was to determine if the pendulum period is dependent on the simple pendulum mass. We also wanted to calculate the relation between average time per simple pendulum period versus the mass of the simple pendulum. Overall, some of the theories that we looked at and referred back to during this experiment included that the period of a simple pendulum is directly proportional to the square root of the quantity length of the pendulum over the acceleration due to gravity. This length can be found by measuring from the center of the mass. This can be found on the pendulum by balancing it using your 2 fingers. Once the pendulum balances and is not falling, you are able to then measure from that point and find the length. If the above principle holds true, then the measured values for the period of the pendulum should not deviate significantly from the value calculated using the equation. The equation, located at the bottom right of the screen, which reads T equals 2 pi square root of L over G. T is equivalent to the period in seconds, L is the length in meters, and G is the gravity acceleration in the units of meters over seconds squared.
The equipment needed to perform this lab experiment are a simple pendulum, weights, specifically 50 grams and 2 100 grams, massless string, the mounting apparatus, and a plastic ruler. To perform this lab experiment, I will tell you the steps for this lab procedure. First, attach the light string to the mounting apparatus in simple pendulum. Then, find the center of mass of the simple pendulum using the plastic ruler. Then, release the simple pendulum from an angular displacement of 10 degrees or less from equilibrium. Then, time 20 complete periods and divide by 20 to find the average time per period. Complete this trial 5 more times, adding weight each time by 0.05 kilograms. Each trial will have 5 runs for a total of 25 runs. Finally, copy the results over to Excel to form calculations and complete graphs. The sources of error that can occur from this experiment are from human, systemic, and environmental error. An example of human error could be from improper setup of the apparatus, tying the string incorrectly or too loosely from the simple pendulum to the apparatus, or inconsistent timing by stopping and starting the stopwatch inconsistently. An example of systemic error would be if the tools were tampered with or faulty. An example of environmental error would be that the gravity constant changes based on the altitude of your location. For example, our gravity constant was 9.7666. So you would have to make sure that you use the appropriate G value for your location.
The next step would be to analyze the data and come up with your results. We analyzed our data in a chart in Excel, which had 3 columns for each of the 3 data values that we had collected for each trial. Those values were the weight of the mass at the end of the pendulum in kilograms, the time for 20 periods in seconds, and the time per period in seconds, which is basically the time for 20 periods divided by 20. We then found the average time per period for each mass that we had used in the experiment, and we compared these average period times to our expected value for the period, which we had calculated using the length of the pendulum from the pivot point at the top to the center of mass of the weight we were using. We plugged that value into the equation that Sophia had mentioned earlier to find our expected value. We also graphed the average time per period versus the mass and the time per period versus the mass, and found the trend line for both graphs. We were looking for a slope close to 0, which would indicate that there was no correlation between the mass at the end of the pendulum and the time per period. In conclusion, we found that the period of a pendulum is in no way related to the amount of mass on the pendulum. Also, our data values were consistent with our expected value for the period of a pendulum. As such, there is no relationship between the mass on a pendulum and the pendulum's period.